A world of fire churns in permanent daylight around Jupiter. This is Io, the most geologically active body in our solar system, a moon where volcanoes rage on a scale that rewrites every rule of geology we know from Earth. Its surface is a canvas of chaos, painted with eruptions that dwarf our own, mountains that walk, and lakes of lava so vast they can be seen from telescopes across space. Your journey here is to witness 30 of its strangest and most baffling phenomena. By the end, you will understand the violent, beautiful engine that powers this alien forge. We will stand at the edge of a lava lake larger than a great sea and watch plumes of gas reach for the stars. What does such relentless fury tell us about the hidden hearts of worlds? Our first stop on this tour of fire is a landmark of such scale it redefines the word volcano. Loki Patera is not a mountain but a wound, a colossal horseshoe-shaped depression in Io's tortured crust. Within its stark walls churns the largest active lava lake known to science, a body of molten rock so vast its surface area rivals that of Lake Ontario. Picture the entire Great Salt Lake, but instead of water, it is a single, roiling sea of incandescent magma. This is not a feature you could simply walk around. It is a geographical province of pure, raw planetary energy. For decades, astronomers have watched this distant forge with fascination, noting a strange and reliable pulse. Roughly every 400 to 500 Earth days, Loki Patera undergoes a dramatic brightening, its infrared signature flaring as if a switch had been thrown deep within the moon. This is not a random explosion, it is a volcanic heartbeat, a rhythm written in fire. The leading theory is as terrifying as it is beautiful. Scientists believe a thin, solid crust forms on the lake's magma sea, a fragile lid over unimaginable heat. Over time, this crust grows, cools, and becomes denser than the liquid rock beneath it. Eventually, a section of this rocky skin becomes unstable, fractures, and sinks. This event, called an overturn, is like pulling a plug from a cosmic drain. A vast slab of crust founders into the abyss, exposing the blindingly bright, fresh magma underneath. The lake's brightness spikes as this new, hotter surface is revealed, a process that may cascade around the Patera in a wave, turning over the entire sea in a months-long cataclysm. Loki's predictable pulse is our clearest window into the tidal heating that cooks Io from within. By timing its beats, we measure the moon's internal furnace, understanding how the gravitational tug of war between Jupiter and its other moons pumps energy relentlessly into this world's core. This lake is not just a wonder, it is a laboratory, a natural engine whose rhythmic churn tells the story of a moon being torn apart and reborn in fire over and over again. Yet Loki's rhythmic churn is not the only landmark painting Io's face from orbit. Look to the southern hemisphere and you will find a signature of a different kind of fury. Here, the volcano Peel does not merely erupt, it exhales. Its most famous feature is not a lake of lava, but a colossal, umbrella-shaped plume that regularly towers over 300 kilometers above the surface. To grasp that scale, picture this: if such a plume erupted from a volcano on Earth, it would reach well into the vacuum of space, dwarfing our atmosphere's very layers. This is an eruption column of almost incomprehensible height, a geyser of alien material blasting from the moon's very soul. What fuels this incredible ascent is not just rock but gas, vast quantities of it. Peel's plumes are composed primarily of sulfur and sulfur dioxide. As this superheated gas erupts into the frigid vacuum of space, an alien alchemy occurs. The gases do not simply dissipate, they freeze almost instantly, crystallizing into trillions of fine, dust-like particles of sulfur and sulfur dioxide frost. This creates a towering cloud of glittering, poisonous snow, a plume that is both beautiful and lethal, and this relentless activity has left an indelible mark. For decades, perhaps centuries, Peel has been spewing this colored fallout. the finest particles settle in a vast, faint ring centered on the volcano itself, staining the surrounding landscape a deep, rusty red. From space, this creates a target like bullseye, a perfect circle hundreds of kilometers wide that screams of persistent, violent activity. It is a landmark painted not by a single cataclysm, but by endless, steady exhalation. This red ring is Peale's autograph on the face of Io, a signature written in frozen sulfur that tells us some volcanoes here do not just explode in fits and starts, they breathe a constant, world-shaping breath. But these plumes of frozen gas are only half the story of Ios volcanic fury. For a spectacle of pure, liquid fire, we must travel to the northern reaches and witness an event that redefined what we thought possible. In 2007, as the New Horizons spacecraft raced toward Pluto, it turned its cameras back toward Jupiter for a gravity assist and captured something breathtaking. At a volcanic complex named Tivashta Katina, a fissure over 60 kilometers long had torn open the moon's skin. From this wound, not a plume of gas, but a curtain of actual molten lava was being hurled into the sky. The incandescent fountain reached an estimated 350 kilometers high, a geyser of pure rock so powerful it was visible from a passing spacecraft millions of kilometers away. Try to hold that image, a wall of lava taller than the distance from Earth's surface to the edge of space, erupting in complete silence into the black vacuum. This was not a slow oozing or a lake overturning. This was a violent, explosive projection of the moon's very blood. Such fire fountains are driven by immense gas pressure. Within Io's magma chambers, volatile gases like sulfur dioxide are dissolved in the molten rock, trapped under incredible pressure. When a fissure opens, it is like uncorking the most shaken bottle of soda imaginable. The sudden drop in pressure causes the gas to come screaming out of solution, expanding violently and blasting the magma into a fine spray of incandescent droplets. The sheer height of Tivashta's fountain tells us the magma there was not just hot, it was packed with an extraordinary amount of these explosive volatiles. It reveals chambers under pressures far greater than anything found in terrestrial volcanoes. Chambers where gas is not a minor component but the primary engine of eruption. This single observation showed us that Io's eruptions are not just larger versions of our own. They are a fundamentally different kind of event, where the vacuum of space and the moon's unique, gas-rich interior combine to create celestial fireworks on a scale we are only beginning to understand. The silent, explosive fireworks of Tivashta are a spectacle of creation, but on Io, every act of creation is also an act of utter destruction. To witness this truth, we must travel to a different volcanic complex and step back in time to a single, transformative year. In 1997, the Galileo spacecraft orbiting Jupiter watched as Patera, a volcano named for a Mapuche god of thunder and fire, unleashed an apocalypse. This was not a tall, graceful plume or a contained lava lake. This was a flood, an immense volume of molten rock, far hotter than the sulfurous flows common elsewhere, burst from the Patera and spread across the landscape like a slow, dark tsunami. Its target was a vast, brilliant plain surrounding the volcano, a region stained a stark white and yellow by centuries of accumulated sulfur dioxide frost. This bright plain was a historical record, a page in Io's geological diary. Then the lava arrived. The fresh, silicate magma from Pilon was incredibly hot, perhaps over 1,500 degrees Celsius. As this black river advanced, it did not simply flow around the bright deposits, it consumed them. The intense heat vaporized the volatile sulfur dioxide frost instantly, stripping the landscape clean and baking the older, colorful minerals into a uniform, dark crust. Within a matter of months, an area larger than the state of Connecticut was utterly transformed, painted over in a fresh coat of stark, featureless black. The speed of this change is what staggers the mind. On Earth, major resurfacing events like large lava flows or caldera formations take centuries or millennia to unfold and then millions of years to erode. On Io, Patera accomplished a complete geological makeover in a single Earth year. It was a blink of an eye in planetary time. This event gave scientists a critical clue. The darkness and high temperature of the flow confirmed it was composed of silicate rock, similar to basalt on Earth, rather than the cooler, sulfur-rich lavas. Pillen showed us that Io's interior is not just a slushy mix of sulfur, but contains a deep, searing core of rocky magma, capable of flooding the surface and erasing entire chapters of history overnight. One year, a bright plain, the next, a dark scar. On this moon, the ground beneath your feet is not just unstable, it is temporary, a page constantly being torn out and rewritten by the planet's relentless inner fire. This relentless cycle of creation and destruction has sculpted a surface unlike any other, but the fire is not the only architect here. Scattered across Io's tortured plains are structures that defy volcanic logic, solitary mountains that soar higher than Everest yet stand utterly alone. They are not part of volcanic ranges, nor are they the cones of ancient, dormant volcanoes. These are the non-volcanic mountains of Io, and their very existence is a profound geological mystery. On Earth, our tallest peaks are born from the slow, grinding collision of tectonic plates, a process that takes millions of years to push rock skyward. Io has no such moving plates. Its crust is a single, global shell, continuously buried under fresh lava and sulfurous frost. So how do mountains taller than any on our planet simply appear? The answer lies in the same global forces that fuel the volcanoes, but with a different, more brutal expression. Scientists believe these mountains are not built from below by rising magma, but from the side by unimaginable compression. Picture the entire crust of Io as a giant global stress ball. Every single day, Jupiter's immense gravity, combined with the tug of other moons, squeezes and kneads this world. This tidal flexing generates heat that melts the interior, creating the volcanoes, but it also puts the crust itself under tremendous, unrelenting pressure. In some regions, this pressure becomes so extreme that the crust cannot simply fold, it must break. Enormous blocks of solid rock, sometimes hundreds of kilometers across, are thrust upward along deep faults, tilting and rising like colossal icebergs of silicate stone through a sea of softer sulfur deposits. They are tectonic orphans born from global squeezing rather than plate collisions, but their story does not end with their birth. These majestic peaks exist in a state of perpetual siege. Io's constant, violent quakes, some of the strongest in the solar system, shake their foundations. Worse, they are bombarded by the very environment they inhabit. The endless snowfalls of sulfur dioxide, frost from plumes like peels settle on their slopes, while corrosive volcanic gases eat away at the rock. Unlike Earth's mountains, which are shaped over eons by wind and water, Io's mountains are being actively, rapidly dismantled. They are transient titans, rising in a geological instant from a global vise, only to be worn down by the very fury that surrounds them. A stark reminder that even the mightiest landmarks here are temporary in the face of the moon's unending torment. These solitary mountains may be slowly crumbling, but elsewhere on Io, the landscape is being built in a spectacle of relentless, liquid persistence. In the moon's northern hemisphere, a river of fire named Anomalies has been flowing for decades, perhaps even centuries. This is not a single catastrophic event, but the longest continuously active lava flow ever observed in our solar system. A fiery serpent over 300 kilometers long, slowly carving its path across the frozen plains. Imagine the entire length of a major river, but instead of water, its channel glows with the incandescent light of molten rock, constantly fed by a source eruption that simply refuses to stop. The Anomalies flow is a masterclass in what volcanologists call effusive volcanism, the relatively gentle, steady outpouring of lava, as opposed to the explosive, gas-driven fury of a plume. It behaves much like the legendary lava flows from Kilauea in Hawaii, where liquid rock oozes from a vent, builds levees along its sides, and advances in slow, glowing lobes. But here, the scale is utterly alien. The Anomalies system dwarfs anything on Earth, with a main channel that would stretch from one major city to the next, fed by a complex network of smaller tributaries and breakout flows that constantly shift and branch. Observations from spacecraft over many years show this colossal flow field is not static. It is a living, changing feature. New breakouts periodically surge from its sides, advancing the flow front by a few kilometers or forging entirely new paths across the sulfurous crust. This slow-motion dance of creation provides a real-time lesson in planetary geology. By watching Anomalies inch forward year after year, scientists can calculate how much new material is being added to Io's surface, measure the viscosity and temperature of its lava, and understand how a steady, persistent eruption can reshape a world over time. It is a river that writes the history of its own making with every meter it travels, a testament to the patient, world-building power of fire that exists alongside Io's more violent explosions. The patient rivers of fire like Anomalies show us one face of Ios volcanism, but there is another, far more elusive side to this world's internal heat. Scattered across the infrared maps of the Moon are dozens, perhaps hundreds, of mysterious pinpricks of intense energy. They appear not as towering plumes or vast lava lakes, but as tiny, brilliant specks of heat against the cold darkness, so small they often leave no visible mark on the surface at all. Scientists call them the black spot volcanoes, and they represent one of the most puzzling categories of activity on this volcanic wonderland. An infrared telescope does not see light, it sees warmth. When trained on Io, these instruments reveal a surface speckled with these incredibly hot, incredibly small points. Each one is a thermal anomaly, a location where the ground is not just warm but searing, often reaching temperatures that suggest exposed fresh magma. Yet when you look at the same location with a regular camera, expecting to see a new caldera or a dark flow, you often find nothing. Just the same old, mottled landscape of yellows, reds, and whites. It is as if the Moon has a fever that breaks out in invisible spots, hot to the touch but leaving no rash. So what are they? The leading theory is that these black spots are tiny, hyperactive lava lakes or open vents. Picture a single, bubbling cauldron of magma, perhaps only a few hundred meters across, exposed directly to the vacuum of space. It would radiate tremendous heat, creating a brilliant infrared signature. But because it is so small and contained, it might not produce enough lava to spill over its rim and create a dark flow that our visible light cameras can see. Alternatively, it could be a persistent fire fountain, a miniature version of Vashta's curtain, constantly spraying incandescent droplets that cool and fall back into the vent, never building up a noticeable deposit on the surrounding plain. Their small size and lack of visible debris make them extraordinarily difficult to study. They are like distant bonfires seen only by their glow, their flames hidden behind a hill. We can measure their heat, but without seeing their structure, we cannot be sure of their exact nature. This is where the true importance of the black spots comes into focus. They are not just curiosities, they are critical clues to Io's total energy budget. Loki Patera and the giant plumes are the headline acts, the dramatic releases of the Moon's internal heat. But these countless tiny black spots may be the background hum, the distributed network of smaller leaks and vents that collectively release a massive amount of energy. Finding and cataloging them is like mapping the capillaries in a body, understanding how the lifeblood of heat is carried to the very surface. They tell us that Ios volcanism is not just about a few dozen spectacular sites. It is a planet-wide fever, a sickness of heat that breaks out anywhere the thin crust cracks under pressure, releasing the fire within in whispers as well as shouts. Yet the quiet hum of black spot volcanoes is only one part of a much broader symphony of fire. To hear a single volcano shift between movements, we must journey to a dramatic location where fire meets ice in a constant, silent war. Wedged dramatically between two colossal non-volcanic mountains, Loki Patera is a volcanic crater with a split personality. Its very setting is a portrait of Eo's duality, a cauldron of molten rock nestled in the shadow of towering, frozen blocks of crust. This volcano does not settle on one style of eruption. It has left evidence of them all, making it a perfect case study in the chaotic heart of this moon. The first personality of Loki is explosive and flamboyant. Spacecraft have captured images of a faint, persistent ring of bright material surrounding the Patera, a telltale bullseye signature of fallout from a high-altitude plume. This ring, similar to Peel's but smaller, tells us that Loki has at times been a gas-driven giant, blasting sulfur-rich particles high into the sky where they freeze and drift down to paint the landscape. This is the classic Io eruption, a spectacle of force and height, but look closer at the floor of the crater itself, and a different story emerges. Infrared observations reveal that Loki Patera often glows with a steady, intense heat. This is not the fleeting spike of an explosion, but the consistent signature of a vast, exposed body of molten rock, a lava lake churning within the caldera's walls. Here, the volcano's second personality emerges, one of patient, seething containment, more akin to the rhythmic overturns of Loki than the violent exhalations of Peel. So how can one volcanic depression host such opposing behaviors? The answer lies deep in the plumbing. Scientists believe Loki possesses a complex, multi-chambered magma reservoir beneath its crater. Sometimes the magma rising to the surface is rich in dissolved gases like sulfur dioxide. When this volatile, rich brew finds a path to the surface, the pressure release triggers a violent explosion, creating the towering plume and its fallout ring. At other times, the magma that reaches the chamber might be slightly different, perhaps lower in gas or arriving through a more passive pathway. This magma can pool quietly, forming a persistent lava lake that radiates heat without the dramatic fireworks. This dual nature suggests that Loki's magma source is not uniform. It may tap into different layers or batches of molten material within Eo's tortured interior, each with its own chemical recipe and gas content. One day, it might draw from a frothy, volatile charged source and the next from a deeper, quieter reservoir. This makes Loki a fascinating window into the complexity beneath the surface. It is not merely a hole where lava comes out, it is a dynamic valve, a junction where different pipelines from the moon's interior can connect, dictating whether the volcano will whisper with a lake of fire or scream with a plume of frost. Its varying consistency is the key to understanding the rich, varied, and utterly unpredictable menu of eruptions that Io serves up across its burning surface. The ever-shifting moods of a volcano like Loki reveal a world of complex plumbing beneath the crust, but some of Io's most mysterious eruptions seem to have no home at all. Across decades of observation, spacecraft and telescopes have occasionally caught sight of immense, towering plumes erupting from locations that were, just months before, utterly quiet. These are the transient plumes, ghostly eruptions that appear without warning over featureless plains, blaze brilliantly for a few weeks or months, and then vanish, leaving behind no obvious volcanic scar to mark their passing. They are wanderers, eruptions without an address, and they represent one of the most unpredictable elements of Eo's chaotic volcanism. One of the most famous examples occurred in the Moon's southern hemisphere. In 1990, the Voyager spacecraft had mapped the region in detail, noting no major volcanic centers. Yet just a few years later, the Galileo probe arrived to find a colossal new plume, over 150 kilometers high, erupting from this very same, apparently inert landscape. It was as if the ground had simply opened up, screamed a jet of gas and dust into the sky, and then closed again, leaving only a faint, temporary stain. So what could possibly fuel such a here-today, gone-tomorrow cataclysm? Scientists point to two compelling possibilities, both rooted in Eo's uniquely tortured geology. The first is the short-lived fissure eruption. Imagine a crack, perhaps dozens of kilometers long, suddenly ripping open in the cold crust. This fissure taps directly into a shallow, pressurized reservoir of gas-rich magma. For a brief, violent period, the volatiles explode outward, creating a spectacular curtain of eruption like the one seen at Tivashta, but perhaps even more gas-dominated. Once the local pocket of frothy magma is exhausted or the fissure seals itself shut from rockfall and cooling lava, the show ends. The fissure might be buried by falling plume debris or subsequent sulfur dioxide frost, becoming invisible to our cameras. The second, even more intriguing idea involves not magma at all, but buried treasure of a different kind. Eo's crust is a layered cake of sulfur and sulfur dioxide frost, silicate rock, and possibly vast subsurface deposits of frozen volatiles. As the tidal forces of Jupiter constantly flex and heat the moon, these buried layers of solid sulfur dioxide could be suddenly warmed. If they transition rapidly from solid to gas in a confined space, the pressure buildup would be catastrophic. The result would be a colossal, explosive venting, a cryovolcanic eruption of gas and ice particles that blasts through the overlying crust. This would be a plume driven purely by the explosion of trapped fumes, a cosmic geyser that empties its reservoir and then falls silent, perhaps for centuries. These wandering plumes force us to confront a humbling truth about Io. Our maps of its active volcanoes are not a complete catalogue. They are merely a snapshot of the loudest, most persistent voices. Beneath the familiar calderas and lava lakes, the entire crust may be a pressurized network of volatile pockets and stress fractures, any of which can blow without precedent. It means that on this moon, an eruption can happen absolutely anywhere at any time. The ground you stand on might be stable for 1,000 years, or it might be the lid on a boiler that is about to burst tomorrow. This omnipresent potential for sudden, planet-wide chaos is what makes Io not just an active world, but a fundamentally unpredictable one. This potential for chaos is written in stone, or rather, in the colossal scars left by eruptions that refuse to be confined. In the Moon's southern hemisphere, the volcano Masubai has not merely erupted, it has flooded the landscape on a biblical scale. Its legacy is not a single river of lava, but a sprawling, fan-shaped complex of overlapping flows that stretches for over 300 kilometers from its source. This is one of the largest single lava flow fields known in our solar system, a dark stain on Io's face so vast it can be clearly seen from interplanetary distances. The Galileo spacecraft provided our most detailed maps of this titanic feature, revealing a history written in overlapping layers of cooled rock. Each dark lobe and channel represents a separate breakout, a time when Masubai's magma found a new path to the surface and poured forth, covering its own older siblings in a fresh coat of black. The entire complex resembles a giant, inverted river delta, but one where the water has been replaced by a slow, relentless tide of molten basalt. Measuring something of this scale presents extraordinary challenges. From orbit, scientists can map its area with relative ease, but determining its volume, the critical number that tells us how much material erupted, requires guessing its average depth. They use the shapes of the flow margins, the steepness of its levees, and comparisons to similar, smaller flows on Earth to make estimates. The numbers they arrive at are staggering, suggesting Masubai has emplaced enough lava to bury a small country under meters of rock. Even more telling is the temperature data. Infrared readings from Galileo showed that parts of the Masubai flow field remained surprisingly hot long after the main eruption phase, indicating the flows were not just vast but also incredibly thick. A thin flow of lava cools quickly against the cold vacuum of space, but a thick, massive flow acts like a thermal blanket, its interior staying molten for years, even decades, slowly releasing its stored heat to the surface. This persistence of warmth is a crucial clue. The sheer volume and retained heat of Masubai's flow field point to an eruption of almost unimaginable duration and power. It was not a brief, explosive event, but a sustained, prodigious outpouring of magma from the depths. To feed such a flood requires a magma reservoir that is not just large but constantly being replenished. The Masubai complex, therefore, is more than a geological wonder. It is a direct measurement of Io's internal furnace. Its existence tells us that the tidal heating process is not just creating pockets of melt, but is capable of generating and sustaining a massive, continuous supply of molten rock, funneling it to the surface in quantities that can resurface entire regions in a single, protracted event. This is the Moon's interior made visible, a testament to the fact that its volcanic capacity is limited not by the availability of magma, but only by where the thin crust finally cracks under the pressure. The colossal lava floods of Masubai create a stark, dark canvas, but across much of Io, the dominant color is not black but a brilliant, blinding white. This is the work of a phenomenon that is both beautiful and utterly alien, the sulfur dioxide snowfields. On Earth, snow is a gentle, quiet process where water vapor in the atmosphere freezes into delicate ice crystals that drift slowly to the ground. On Io, snow is a violent, planetary-scale weather event born directly from volcanic rage. When a giant plume like Peel's erupts, it blasts immense quantities of sulfur dioxide gas high above the surface into the Moon's extremely thin atmosphere. In the frigid vacuum of space just a few kilometers up, this gas encounters a radical change. There is no gradual cooling here, no clouds forming. The sulfur dioxide encounters temperatures so low that it cannot remain a gas. Instantly, it undergoes a process called deposition, skipping the liquid phase entirely and freezing directly into trillions of microscopic, solid crystals. This creates a blizzard of fine, glittering frost that then rains silently down across hundreds of kilometers of landscape. The result is a blanket of pure, bright white, a fresh coat of paint that can cover entire mountain ranges and plains. But this is a temporary beauty. Io's surface is a battlefield between this falling frost and the rising fire. A new snowfield might gleam under Jupiter's light for only a short time before a dark lava flow from a distant volcano like Pilon creeps over the horizon, its searing heat vaporizing the frost on contact, baking the ground back to a dark, rocky crust. Or more subtly, the snow might be stained by the colorful fallout from a different kind of plume. If a volcano erupts sulfur gas instead of sulfur dioxide, the resulting particles can be yellow, orange, or red. These colored flakes mix with the white sulfur dioxide frost, creating the pastel yellows, ochres, and rusty reds that give Io its distinctive, mottled palette, like a watercolor painting left in the rain. The snowfields, therefore, are not a permanent feature. They are the fresh page in an endless cycle. They represent a moment of quiet deposition between eruptions, a brief, bright winter that is always waiting to be scorched away or painted over by the next outburst from the world's unquiet heart. This constant interplay between white frost and dark lava, between freezing fallout and molten rock, is what creates the stunning, ever-changing mosaic we see from space, a portrait of a world caught between ice and fire, where the weather itself is forged in the volcano's throat. But this constant snowfall of frozen gas does more than just paint the surface. It also acts as a chilling blanket, one that can temporarily smother even the fiercest fires. This leads us to a phenomenon that reveals the restless, shifting nature of Io's volcanic heart. On a world where lava lakes span hundreds of kilometers, you might assume the center of the inferno is fixed, a permanent fixture within its caldera walls. Yet careful observation tells a different story. Within several of Io's massive volcanic depressions, the primary seat of activity, the most intense point of heat, does not stay put. It moves. Scientists watching these patera over months and years have seen the brightest, hottest spot within a single caldera shift position, sometimes by tens of kilometers. It is as if the lava lake itself is a living thing crawling slowly across the floor of its prison. How is this possible? The leading explanation involves the complex, fragile architecture just beneath the crust. A patera is not simply a bowl filled with magma. It is a collapse feature over a network of underground chambers and conduits. Think of it like a thin plaster ceiling above several interconnected rooms, all filled with molten rock. The active lava lake on the surface is simply where the plaster has fallen through, creating a skylight into the chaos below. Now imagine one of those openings begins to clog. Falling debris from the caldera walls or the cooling and solidification of lava itself can seal off a vent. The magma, still under immense pressure from below, does not stop. It seeks the path of least resistance. It may force its way up through a weaker section of the crust a few kilometers away, punching a new hole and establishing a fresh, incandescent lake. The old lake cools and darkens, its surface crusting over while the new one blazes to life. Alternatively, the entire crustal block forming the caldera floor might be slowly, unevenly subsiding as magma drains from beneath it. Different sections sink at different rates, and as one area founders, it can tap more directly into the upwelling magma, becoming the new hotspot. This migration is a powerful reminder of the dynamic forces at play just out of sight. It means that even when we identify a specific volcano as active, we cannot assume we know exactly where on that volcano the fury will be concentrated next year or even next month. The fire is searching, probing the thin shell of rock that contains it, always looking for a new way out. A caldera is not a static container. It is an active battlefield where the molten interior wages a constant, silent war against the solid surface, winning ground in one area only to retreat from another, ensuring that the landscape of fire is never, ever still. This restless fire does not just reshape the ground it breathes. Every plume and gas vent on Io is exhaling directly into space, creating an atmosphere so thin and temporary it must be constantly remade. Unlike Earth's thick, permanent blanket of air, Io's atmosphere is a fugitive shroud, a wispy layer of sulfur dioxide and other gases that would vanish in mere days if the volcanoes ever fell silent. It is a ghost sustained only by endless eruptions, a breath held by a world in perpetual scream. But this tenuous breath is caught in a cosmic gale. Jupiter possesses the most powerful magnetic field in the solar system, a spinning dynamo of invisible force that engulfs its inner moons. As Io orbits, it plows through this field at tremendous speed, and the effect is like holding a leaf in a hurricane. The charged particles and intense magnetic forces act as a planetary sandblaster, relentlessly stripping atoms and molecules from the top of Io's atmosphere. This stolen material does not simply disappear. It is swept up and accelerated, forming a vast, donut-shaped cloud that traces Io's entire orbital path around Jupiter. Scientists call this the neutral cloud torus, a ring of primarily sulfur and oxygen atoms that shares the Moon's journey, a ghostly collar of lost atmosphere. Picture the wake of a speedboat, a trail of churned water that lingers long after the boat has passed. Io's neutral cloud is its atmospheric wake, a faint but persistent sign of the brutal erosion happening every second. This cloud is the first step in a chain reaction of staggering scale. The neutral atoms in the torus are peaceful, electrically balanced, but swimming through the violent sea of Jupiter's magnetosphere, they don't stay that way for long. They are bombarded by high-energy particles which rip electrons away, transforming them from neutral atoms into charged ions. This process of ionization is the ignition of a far greater phenomenon. Once charged, these sulfur and oxygen ions become trapped by Jupiter's magnetic field lines. They are whipped around the planet, gaining tremendous speed and energy, collectively forming a gigantic, donut-shaped ring of superheated plasma that glows with an invisible, intense light. This is the Io plasma torus, one of the most brilliant features in the Jovian system when viewed in ultraviolet light. It is a direct physical connection between a moon's volcanic fury and the physics of a gas giant's space weather. The sulfur that erupts from a vent like Peel can within days be torn from the atmosphere, ionized, and injected into this colossal particle accelerator, fueling auroras on Jupiter itself and influencing the radiation environment for every other moon in its neighborhood. The volcanoes are not just surface features, they are the pistons of an engine whose exhaust fills an entire planetary system. The invisible breath of Io's atmosphere is a direct product of its heat, but that heat leaves its own ghostly signature long after the fires have died. When a colossal flow like Masubai finally stops advancing, the spectacle is over for our eyes. The incandescent glow fades, the fresh black crust solidifies into a featureless plain. Yet in the infrared spectrum, the story is just entering a new chapter. This is the world of thermal echoes, the lingering warmth that whispers secrets about the eruption long after it has fallen silent. By tracking how quickly a lava flow cools, scientists can decode its hidden history, turning a simple temperature reading into a detailed geological report. Think of a freshly poured cup of coffee. A thin layer on a saucer will cool to room temperature in minutes, but a full, thick mug will stay warm for hours. The same physics governs the cooling of lava on Io, but on a planetary scale and in the perfect insulation of a vacuum. When a spacecraft like Galileo or Juno points its infrared instruments at a recent flow, it isn't just seeing a hotspot, it is capturing a cooling curve. The rate at which that spot's temperature drops over days, months, and years is a thermal fingerprint. A flow that cools very quickly likely means it was thin, perhaps only a few meters deep. Its entire volume was exposed to the cold of space and radiated its heat away rapidly. But a flow that remains detectably warm for years, even decades, tells a very different tale. It must be extraordinarily thick, perhaps tens or even hundreds of meters deep. That immense volume of molten rock acts as its own insulator, with only the surface crust cooling while the interior remains a simmering reservoir of heat, slowly releasing its energy upward. This is how we know the Masubai flow field is not just a wide stain, but a profound depth of material. Its persistent thermal echo is the cry of a buried ocean of magma, still cooling beneath a solid skin. But the cooling curve reveals more than just size, it hints at the lava's very recipe. Not all lava on Io is the same. Some eruptions, like the dark floods from Pilon, are driven by searing hot silicate magma, similar to Earth's basalt. This rock melts at over 1,200 degrees Celsius. Other flows may be composed of molten sulfur or sulfur compounds, which erupt at much lower temperatures, perhaps only 200 or 300 degrees. An infrared sensor can measure the starting temperature of a flow as it begins to cool. A thermal echo that starts incredibly hot and fades slowly points directly to silicate lava. An echo that starts warm and fades quickly could indicate a sulfur flow. By reading these thermal signatures, scientists can map the underground plumbing without ever drilling a hole. They can identify which volcanoes are tapping the deep, rocky mantle and which are erupting material from shallower, sulfur-rich layers in the crust. The final piece of the puzzle is the insulation provided by Io's own strange landscape. The surface is not bare rock, it is often blanketed by that fine, fluffy snow of sulfur dioxide frost. This frost is a fantastic insulator. A new lava flow might quickly become buried under subsequent snowfalls from nearby plumes. This blanket of frost would dramatically slow the cooling process, trapping the heat beneath it like a planetary thermos. A thermal echo that persists far longer than the flow's thickness alone would predict is a strong signal that the volcano's own snowy weather is helping to preserve its warmth. So a single, fading point of heat on an infrared map becomes a rich data source. It tells us the eruption was thick, it was made of rocky magma, and it is now buried under a protective layer of frost. Each thermal echo is a memory of fire, etched into the cold ground, waiting for the right instruments to listen and understand the full story of the cataclysm that created it. These ghostly signatures remind us that on Io, an eruption's end is not an end at all, but merely a transition from a violent spectacle to a slow, silent confession of everything that happened below. These lingering thermal echoes are the whispers of past eruptions, but sometimes Io does not whisper. It screams. Across decades of monitoring, a handful of volcanic events have stood out not for their location or their plume height, but for their sheer, raw, explosive power. Astronomers label them outburst eruptions, and they are the closest thing this volcanic moon has to a super event, a paroxysm that rewrites the local landscape in a single, violent spasm. An outburst is not merely a big eruption, it is a fundamental change in state. A volcano that typically glows with a thermal output of, say, 100 gigawatts might suddenly flare to 10,000 gigawatts, an increase of 2 orders of magnitude in a matter of hours. It is as if a familiar bonfire suddenly transformed into a nuclear detonation. The entire thermal signature of the moon can spike measurably from Earth-based telescopes because of a single one of these events. So what force could possibly trigger such a staggering release of energy? The theories point to catastrophes in the hidden plumbing. One compelling idea involves the catastrophic collapse of a magma chamber roof. Picture a vast underground sea of molten rock, perhaps dozens of kilometers across, resting under a ceiling of solid silicate rock. The tidal stresses constantly flexing Io slowly weaken this ceiling over time. Finally, a critical point is reached. A huge section of the roof gives way, foundering into the magma chamber below. The effect is twofold. First, the sudden collapse exposes a colossal surface area of fresh, incandescent magma to the vacuum, creating an instantaneous and enormous thermal flare. Second, and more violently, the collapse displaces the magma. It is like dropping a boulder into a pond, but the pond is molten rock under immense pressure. The displaced magma is forced violently upward through every available crack and fissure, erupting at the surface not as a single flow, but as a simultaneous, frenzied network of fire fountains and floods. The result on the surface would be apocalyptic, a rapid, chaotic resurfacing of an area hundreds of kilometers wide. Another, even more volatile theory involves a meeting of 2 alien worlds beneath the crust. Imagine a large, conventional magma chamber of silicate rock slowly migrating upward. Unknown to it, directly in its path lies a gigantic, buried reservoir of solid sulfur dioxide, a frozen lake of volatiles sealed under pressure. When the searing hot magma intrudes into this icy vault, the result is not a merger but a titanic explosion. The solid sulfur dioxide does not melt, it flash vaporizes. In an instant, it transforms from a solid into an immense volume of gas, expanding with unimaginable force. This is a fuel-air explosive on a planetary scale. The resulting blast would shatter the overlying crust, ejecting a mixture of vaporized frost, shattered rock, and magma high into space, while likely draining the magma chamber itself in a furious, short-lived flood. An outburst eruption of this type would be a hybrid event, part volcanic, part cryovolcanic, a true meeting of fire and ice that leaves a scar unlike any other. These super events are rare, but their potential existence tells us that Io's volatility has an upper limit we have yet to fully witness. They represent a geological breaking point, a moment when the built-up strain and volatile pressure can no longer be released in steady streams or rhythmic pulses, but must instead tear the world open in a single, shattering release. To witness one would be to see the moon's interior turn itself inside out, if only for a day. The explosive fury of an outburst eruption is a planetary scale event, but the war between fire and ice is fought in 1,000 smaller, daily battles across Io's surface. One of the most dramatic and alien of these conflicts occurs wherever a river of lava meets a field of frozen sulfur dioxide. On Earth, lava flowing into the ocean creates violent steam explosions, a meeting of water and fire. On Io, the interaction is colder, stranger, and just as violent. Here, the opponent is not liquid water, but a blanket of solid frost that behaves like a cosmic explosive. Picture the relentless advance of a dark, glowing lava flow, its leading edge a wall of rock over 1,000 degrees Celsius. Before it lies not bedrock, but a vast, brilliant plain of sulfur dioxide snow, deposited by a distant plume and as cold as the vacuum itself. The moment the two make contact, physics takes a radical turn. The intense, radiant heat from the lava does not simply melt the frost. In the near-perfect vacuum of Io's surface, the sulfur dioxide undergoes a process called explosive sublimation. It bypasses the liquid state entirely, transforming instantly from a solid crystal into an expanding cloud of high-pressure gas. This is not a gentle steaming, it is a sudden, violent decompression. The conversion from solid to gas causes a massive, rapid increase in volume, as if a buried balloon had been inflated all at once. This expanding gas has to go somewhere, and it does so with tremendous force. It can blast upward through the crust of the advancing lava flow itself, fragmenting the solidifying rock into shards and throwing them into the air. It can also burrow backward under the flow, lifting sections of the molten river on a cushion of gas and causing the front to break apart into chaotic, blocky lobes. The result is a scene of magnificent, destructive chaos. The smooth, predictable advance of the lava is shattered. The flow front becomes a ragged, fractured line of tumbling rock and sudden gas jets. Plumes of sulfur dioxide vapor, invisible to our eyes but detectable to instruments, erupt from beneath the flow, further disrupting its path. This interaction carves a uniquely Io-like signature into the landscape. Instead of the smooth, ropey textures of a Hawaiian paho, ho flow, or the blocky rubble of an ah flow, we get something more jagged and explosive. The terrain where lava meets frost becomes a zone of pits, disrupted plates, and scattered debris, a testament to the ground literally blowing out from under the lava's own weight. This process, repeated across countless flows over eons, is a primary architect of Io's famously rugged and chaotic terrain. It means that even a gentle, effusive eruption can be transformed into a locally explosive event, not by gases from within the magma, but by the very ground it is trying to cover. The Moon's surface is not a passive canvas, it is an active reactant, a layer of frozen volatiles waiting to detonate on contact with the world's inner heat. In this endless, silent war, every new lava flow must conquer not just distance, but the land itself, a land that fights back with the sudden, explosive breath of its own icy mantle. The explosive encounters between lava and frost create a landscape of chaos, but not every volcano on Io is engaged in such violent conflict. Some burn with a quieter, more patient flame. In the Moon's equatorial region, Ios Patera has been a steady, unwavering ember in the infrared sky for as long as we have been watching. Unlike the rhythmic, dramatic overturns of Loki or the towering plumes of Peel, Ios does not scream for attention. It simply glows, a consistent point of moderate heat that has persisted for decades without dramatic flare-ups or catastrophic collapses. This is the phenomenon of steady-state volcanism, and it reveals a different kind of stability amidst the global frenzy. What does it mean for a volcano to be so reliably, quietly active? The leading explanation points to a remarkably stable system beneath the caldera. Ios Patera may host a lava lake that is in a near-perfect state of continuous convection. Imagine a pot of thick soup on a very low, consistent heat. The soup at the bottom, closest to the heat source, warms up, becomes less dense, and rises slowly to the surface. At the surface, it cools slightly, releases its heat into the air, becomes denser, and then sinks back down the sides to be reheated. This creates a slow, rolling circulation that keeps the entire pot at a roughly even temperature. At Janus, the pot is a lake of magma, and the stove is the relentless tidal heating from Jupiter's gravity. The convection cycle may be so efficient and balanced that the lake never develops a thick, unstable crust that would lead to a dramatic overturn event. Instead, it constantly renews its surface in a gentle, rolling motion, radiating a steady thermal signature year after year. An alternative, or perhaps complementary, model suggests Janus sits atop a magma conduit that acts like a permanent, open artery. Deep within Io, a constant upwelling of molten rock rises through a stable, insulated pipeline directly to the surface. This conduit is never blocked by falling debris or solidified plugs. It simply delivers a continuous, modest supply of fresh, hot magma to the Patera floor, where it pools, cools, and releases its heat at a constant rate. This makes Janus less of a lake and more of a volcanic spring, a steady drip of planetary heat that never floods but also never runs dry. The importance of Janus Patera cannot be overstated. While we are naturally drawn to the spectacular outbursts and wandering plumes, this kind of persistent warmth represents the true background hum of Io's volcanic activity. It is the baseline energy output. Think of Io's total volcanic power as a symphony. The outburst eruptions are the cymbal crashes, the giant plumes are the blaring trumpet fanfares. But the long, sustained note of a cello, the underlying rhythm of the percussion, that is Janus. You cannot have the dramatic moments without the constant, supporting foundation. These steady-state volcanoes are critical for balancing the Moon's thermal budget. They act as reliable pressure valves, constantly bleeding off a portion of the internal heat generated by tidal flexing. This may actually prevent even more catastrophic, system-wide outbursts by ensuring the strain never builds to a single breaking point. Janus teaches us that on a world defined by violence, endurance is its own kind of power. Its quiet, decades-long glow is a testament to a fire that does not need to explode to be profound, a reminder that some of the most telling stories are told not in shouts, but in a whisper that never ceases. This quiet, constant glow from volcanoes like Janus provides the background heat, but it is the cold touch of space that paints Io's most vivid portraits. The Moon's stunning palette of yellows, reds, whites, and blacks is not a fixed landscape. It is a dynamic chemical canvas, constantly being repainted by the twin brushes of volcanic heat and cosmic radiation. Every color tells a story of transformation, a fleeting moment in a cycle of creation and decay. When a fresh flood of lava, like the one from Patera, spills across the plains, its first impression is one of absolute darkness. This is the black of newly cooled silicate rock, the purest form of the Moon's interior laid bare. The lava is so hot, often over 1,200 degrees Celsius, that it has not yet interacted with the corrosive environment. It is a blank, dark slate, but Io does not let anything stay pure for long. As this black crust sits exposed, it begins a slow, colorful metamorphosis. Bombarded by the intense radiation trapped in Jupiter's magnetic field and dusted by the endless snowfalls from plumes, the surface chemistry begins to shift. This is where the yellows and oranges emerge. The primary artist here is elemental sulfur. When sulfur is deposited from a plume or cooked out of the crust by subsurface heat, it starts in a simple, pale yellow form. But the relentless radiation does something extraordinary. It breaks the bonds between sulfur atoms and encourages them to link together into longer, more complex chains, a process called polymerization. Think of it like taking single pearls and stringing them into a necklace. Each new configuration of sulfur atoms reflects light differently. As the chains grow longer and more complex, the color deepens, shifting from a pale lemon yellow to a rich, buttery orange, and finally into a deep, rusty red. This is why you often see rings of color around volcanic vents, with the freshest, most irradiated deposits at the center showing the deepest reds, fading out to oranges and yellows further away. It is a natural color gradient etched by radiation dosage. Then there is the brilliant white, the cleanest color on this dirty world. This is the signature of pure, unadulterated sulfur dioxide frost. When a plume like Peel's blasts its gas high into the sky, the sulfur dioxide freezes into tiny, perfect crystals that fall like glittering snow. This frost is so fine and reflective that it creates vast, brilliant plains and caps on mountains, a stark contrast to the colorful sulfur and dark lava. But its purity is an illusion of timing. This white is the most temporary color of all. A nearby lava flow can vaporize it in an instant, or over time, the relentless radiation can break apart the sulfur dioxide molecules, freeing the sulfur atoms to begin their own slow journey toward yellow and red. The surface of Io, therefore, is a living map of activity and age. A bright white area is a recent snowfall, a quiet zone. A patchwork of yellows and reds indicates older, stable terrain that has been thoroughly processed by radiation. A stark black flow is a brand new event, a wound so fresh it has not yet begun to scar with color. By reading this canvas, scientists can date surfaces without a single physical sample. They can trace the fallout patterns of plumes, understand the radiation environment, and watch the literal aging of the ground in real time. It is a world where geology and chemistry perform a continuous, silent dance, and the ever-shifting hues are their only music. This living canvas of color tells a story of surface chemistry, but some of its darkest markings tell a different, more cryptic tale. Stretching like long, black scars across the bright plains are lava flows of extraordinary length, some extending over 500 kilometers from their suspected source. Yet when scientists trace these rivers of cooled rock back to their point of origin, they often find a puzzling void. There is no obvious central caldera, no towering volcanic cone, not even a clear fissure to mark where the fire began. This is the curious case of the dark flow emplacement, a phenomenon that forces us to rethink how lava travels across this alien world. How does a flood of molten rock, enough to fill a valley for hundreds of kilometers, have no clear beginning? The answer may lie not in explosive vents, but in hidden highways. On Earth, in places like Hawaii, we see a process that could provide a clue. When a surface lava flow begins to cool, its outer crust can solidify while the molten interior continues to race forward, insulated from the cold air. Over time, this can form a lava tube, a subterranean pipeline of rock with a roof of solid basalt and a river of fire flowing within. These tubes allow lava to travel phenomenal distances with minimal heat loss. On Io, where the thermal contrast between molten rock and the frozen surface is even more extreme, this process could be supercharged. A major eruption from a known volcano might initially produce a surface flow. But as the crust quickly solidifies in the vacuum, it could roof over, creating an insulated conduit. The lava then travels underground for hundreds of kilometers, completely hidden from view, before finally bursting out onto the surface at a distant weak point. What we map as a single, long flow might actually be the final, emerging segment of a vast, hidden plumbing system. The source vent, now inactive and perhaps buried under debris or frost, becomes invisible to our cameras. The flow appears to emerge from nowhere, a mystery with its beginning erased. Another possibility points to scale so vast it defies simple detection. Imagine not a single point-like vent, but a fissure eruption of staggering length, perhaps 100 kilometers long, tearing open the crust. For a brief, violent period, lava fountains along its entire length, feeding a flood that spreads outward. Once the eruption ends, the intense cold and constant bombardment of sulfur dioxide snow act with startling speed. The fragile edges of the fissure collapse. Volcanic debris and bright frost rapidly fill in the linear depression. Within a few years, the entire fissure, the very wound that birthed the flow, could be completely buried and smoothed over, leaving only the dark, difficult-to-erase stain of the lava flow itself as evidence. The source vanishes, camouflaged by the moon's own relentless weather. These dark, sourceless flows challenge the comforting idea of point source volcanism, where every river of fire leads back to a single, identifiable volcano. Instead, they suggest a world where lava can move like groundwater, traveling secretly through tunnels before revealing itself, or where eruptions can be so geographically diffuse that their origins are literally paved over by the planet's own processes. It means that the dark stains we see may only be the visible tips of much larger, hidden systems, and that the true architecture of Eo's fury is often concealed, written in passages that run deep beneath the colorful, ever-changing skin. The hidden highways of dark lava reveal a world of subsurface secrets, but the true breath of this moon comes from the skies above. Eo's colossal volcanic plumes are far more than just spectacular displays. They function as the very heart and lungs of the moon's fleeting atmosphere. Each towering eruption, like the great exhale of Peel, acts as a planetary-scale atmospheric pump, forcing gas into the void and setting the rhythm for a global cycle of creation and escape. Without these relentless volcanic pulses, Eo's wispy shroud of gas would vanish into the blackness of space in a matter of days. The primary fuel for this system is sulfur dioxide. When a plume erupts, it blasts millions of kilograms of this gas high above the surface at speeds exceeding 1 kilometer per second. This is not a gentle diffusion, it is a violent injection, a geyser directly filling the atmospheric reservoir. For a brief, localized moment, the atmospheric pressure near an active plume can spike dramatically, creating a temporary, volcano-shaped bubble of denser gas. This is an atmosphere being born in real time, erupting from the ground up, but the story does not end with the injection. On the blistering day side of Io, bathed in relentless sunlight, the sulfur dioxide molecules are energetic and remain a gas. Yet as this atmospheric gas is carried by global winds to the frigid night side, a profound change occurs. In the shadow of Jupiter, temperatures plummet to some of the coldest in the solar system. Here, the sulfur dioxide gas cannot remain airborne. It condenses directly into solid frost, falling silently to the surface as the brilliant white snowfields we see. This is the atmosphere literally freezing out, collapsing onto the ground. The entire nightside hemisphere becomes a cold trap, a giant sink where the atmosphere deposits itself as frost. Then, as the region rotates back into sunlight, the frozen frost on the surface is warmed. It sublimates, turning directly back into a gas, rejoining the atmospheric cycle. This creates a daily heartbeat, a sublimation-driven flow of gas from the warm day side to the cold night side and back again. But the pump of the plumes must constantly work against a powerful enemy, escape. The combination of Eo's low gravity and the intense battering from Jupiter's magnetosphere strips atoms away continuously. The plumes, therefore, are in a race against time and space, desperately replenishing what is being lost. This makes Eo's atmosphere uniquely and directly coupled to its volcanic activity. It is not a permanent, buffered system like our own. Its pressure, its density, its very existence rise and fall with the volcanic tempo. A major outburst eruption could temporarily double the atmospheric mass, while a period of relative quiet across several big volcanoes might cause it to thin noticeably. We are witnessing an atmosphere that is not a static environment, but a verb, an ongoing process. It is the immediate, gaseous echo of the fire below, a breath sustained only by a world's endless, screaming effort to cool itself down. This breathless cycle of gas and frost shapes the surface, but the true architecture of Eo's fury is etched in lines that run for hundreds of kilometers. These are the catenary, long chains of pits and collapsed depressions that stitch across the landscape like the scars of a giant's claw. They are not random cracks, but the direct handwriting of the tidal forces that torture this moon from within. and they often become the stage for the most spectacular eruptions imaginable. A catena forms when the global stress on Io's crust becomes too much to bear in a particular region. As Jupiter and its other moons pull and squeeze, the brittle silicate crust can fracture along deep, linear faults. Think of bending a sheet of ice over a curved surface. Eventually, it will develop a long, straight crack. On Io, that crack doesn't just sit at the surface. It can penetrate downward, tapping into buried reservoirs of magma or vast pockets of volatile ices like sulfur dioxide. Once this underground connection is made, the catena becomes a zone of profound instability. Magma can intrude into the fracture, heating and weakening the roof from below, or subsurface volatiles can be vaporized by internal heat, causing the ground above to collapse. The result is a chain of connected pits, each one a sinkhole where the ground has fallen into a void below. They are not volcanic calderas built by explosion, but collapse features created by withdrawal or subterranean melting. The most famous of these linear wounds is Tivashta Catena, the very site of that staggering 350-kilometer high lava curtain witnessed by New Horizons. This catena is a fissure system over 60 kilometers long, a ready-made highway for magma. When the pressure built in the chambers beneath it, the entire length of this pre-existing weakness became a conduit. The crust didn't need to rip open a new vent, it simply utilized the grandest fault line available. The eruption poured forth along the catena's length, turning a geological scar into a river of fire. This reveals a critical principle of Eos volcanism. The catenae are the planet's pressure release valves, its built-in fault lines. They provide the path of least resistance for the moon's internal energy. An eruption doesn't have to blast through fresh, solid crust. It can simply reopen an old wound. This means that once a catena forms, it becomes a permanent weak spot, a recurring site of activity for millennia. Future eruptions will likely follow the same line over and over as magma exploits this permanent highway to the surface. So these long, dark chains are more than just curious surface features. They are the blueprints for future cataclysms, the predetermined tracks along which Eo's fire will inevitably race again, writing its history of heat along the same indelible lines. The long, dark lines of the catenae map the surface stress, but to understand what is actually erupting from those wounds, we must listen to a different kind of signal, one beamed from Earth. For decades, astronomers have pointed not just optical telescopes, but powerful planetary radar systems toward the Jovian system. When these radio waves bounce off Io and return, they carry a hidden message in their strength. Some of the moon's vast lava flows do not just appear dark to our eyes, they shine with an unexpected brilliance in radar light. These radar-bright deposits present a compelling new layer to the mystery of what exactly is flooding out of this world. In radar science, brightness equates to roughness. A smooth surface, like a calm lake or a fresh asphalt road, reflects radar waves away in a single, coherent beam, appearing dark to the receiving antenna. A rough, blocky, chaotic surface, however, scatters the radio energy in all directions, sending a significant fraction back toward the source, creating a bright signature. On Io, some of the most extensive flow fields, particularly those associated with massive eruptions like the one at Masubai, show this pronounced radar brightness. The immediate interpretation is one of texture. These could be flows that cooled into a landscape of incredible jaggedness, a terrain of shattered plates, broken rubble, and steep, ragged cliffs at the scale of the radar's wavelength, which is several centimeters to meters. Such a surface would naturally scatter radar efficiently. This rough texture itself tells a story of eruption dynamics, perhaps of extremely thick, pasty lava that fractured as it moved, or of flows that underwent explosive interactions with subsurface frost, turning their surfaces into fields of jagged debris. But there is another, more profound possibility lurking within that radar echo. The brightness could be a clue to the lava's very recipe, its fundamental chemistry. On Earth, not all lava is the same. The most common type we see, like in Hawaii, is basalt, but there exists a more primitive, older family of lavas known as ultramafic compositions. These are lavas extraordinarily rich in iron and magnesium, and they behave differently. They erupt at even higher temperatures, and critically, they have a lower silica content, which makes them less viscous. When ultramafic lavas cool, they can form distinctive, coarse-grained textures and often develop a rougher, more crystalline surface that could appear exceptionally bright to radar. If the radar bright flows on Io are not just rough, but are composed of this ultramafic material, the implications are staggering. It would suggest that Ios volcanoes are tapping magma that comes from a part of the mantle that has not been extensively processed or differentiated. It would be a direct sample of the Moon's most primitive, ancient interior, material that has remained largely unchanged since Io's formation billions of years ago. On most rocky worlds, including Earth, the mantle undergoes complex cycles where heavier elements sink and lighter ones rise, creating layered and varied magma sources. For Io to be spewing ultramafic lava implies its tidal heating is so intense and so efficient that it can melt the deepest, most primordial rock and bring it directly to the surface at a staggering rate before it has time to settle or differentiate. The volcanoes would not be just surface features, they would be geochemical elevators, delivering the unaltered heart of the Moon directly into the cold vacuum of space. Each radar-bright deposit becomes a potential treasure chest, a frozen snapshot of the raw material from which not just Io, but perhaps all the inner rocky worlds were first forged. Yet the radar-bright flows are just one piece of a much larger and far more baffling thermal puzzle. Io radiates an almost unbelievable amount of energy into space, a continuous infrared scream that defies easy explanation. The total heat flowing from its surface is staggering, exceeding the combined output of every single volcano, mid-ocean ridge, and geothermal spring on Earth. This Moon, smaller than our own, is a powerhouse that outshines our entire planet in volcanic fury. But when scientists sit down with their models of tidal friction, the very process that should be cooking Io from within, they face a profound discrepancy. The math, while powerful, struggles to account for the sheer intensity of the fire we observe. This is the global heat flow paradox, and it suggests our understanding of this tortured world is still incomplete. The principle of tidal heating is sound. As Io is relentlessly squeezed by Jupiter's gravity and the orbital tugs of Europa and Ganymede, its interior flexes like a ball of clay being kneaded. This friction generates immense heat, melting rock and driving the volcanism. The models predict a certain amount of energy based on Io's orbit, composition, and internal structure. Yet the actual measured heat collected by telescopes and spacecraft consistently comes in higher. It is as if we calculated the maximum output of a car engine, only to find the vehicle producing twice the horsepower on the dynamometer. Something is missing from the equation, an extra source of warmth or a more efficient way of generating it. One compelling possibility is that Io's interior is not just partially molten in pockets, but is a global, slushy ocean of magma. Imagine not just isolated chambers of liquid rock, but an entire mantle that is a churning, semi-solid sea. This vast, worldwide reservoir of molten material would have an immense capacity to store and then radiate tidal heat. The friction would be generated not just at discrete boundaries, but throughout the entire viscous volume, cooking the Moon far more efficiently than if it had a solid, rocky mantle with only liquid pockets. A global magma ocean would also explain the sheer ubiquity of volcanism, providing a ready supply of melt to any crack that reaches the surface. Alternatively, the tidal heating process itself might be more complex and efficient than our current models assume. The models often treat Io as a relatively uniform, layered body. But what if its interior is far more heterogeneous, laced with layers of varying stiffness and composition? Certain materials, when flexed, generate more heat through friction than others. A layer of particularly viscous or fractured rock deep within the mantle could act as a super-efficient heating element, concentrating the tidal energy and turning it into an intense, localized furnace that then floods the upper layers with extra heat. It is also possible that the orbital resonances between Io, Europa, and Ganymede are driving the Moon into an even more extreme, elliptical path than we realize, maximizing the tidal stretching and squeezing with every orbit. This paradox is not merely an academic curiosity. Pinpointing the source of every watt of Io's radiated heat is a major scientific goal, a detective story written in infrared light. The effort involves meticulously cataloging every thermal source, from the giant lava lakes and long rivers of fire down to the faintest black spot volcanoes. It is a planetary accounting project, adding up the contributions of the loud, obvious eruptions and the quiet, background whispers to see if they match the total bill. If they do not, the missing heat points directly to something hidden, a deep, global process we have yet to fully map. Solving this mystery would tell us not just about Io, but about the fundamental limits of tidal heating as an engine. It reveals how a world can be transformed when the forces of gravity are applied with unrelenting cosmic force, and hints that even in a system of fire and chaos, the deepest secrets are still written in the language of heat, waiting to be decoded. This immense, constant heat flow powers an atmosphere with a daily rhythm of life and death. Every single evening on Io, as the Terminator line sweeps across the plains, the world does not simply grow dark, it begins to suffocate. The thin veil of gas that erupted from volcanoes just hours earlier faces a sudden, profound crisis. With the sun gone, temperatures on the night side plummet to some of the lowest in the solar system, a bitter cold that can dip below -180 degrees Celsius. In this deep freeze, the very physics of the atmosphere changes. The sulfur dioxide molecules that were energetic gas particles during the day suddenly lose their thermal vigor. They can no longer resist the pull of the Moon's gravity or maintain their gaseous state. Instead, they undergo a rapid, wholesale condensation. Billions upon billions of these molecules slow down, link together, and freeze directly onto the cold surface as a fresh layer of brilliant white frost. This is not a gentle settling of dew, it is the catastrophic collapse of an entire sky. The atmospheric pressure on the night side may plummet by a factor of 10 or even 100 compared to the day side. In practical terms, what was a wispy shroud becomes almost a perfect vacuum. For any hypothetical observer standing in that darkness, the sky would not just be black, it would be utterly, starkly empty. The faint glow of Jupiter light would shine down onto a silent, frozen landscape with no medium to scatter it, no haze to soften it. The world quite literally holds its breath. This daily freeze-out creates a dramatic atmospheric tide. Gas is constantly flowing from the warm, high-pressure day side toward the cold, low-pressure night side, only to freeze out and vanish upon arrival. It is a planetary-scale circulation driven by sublimation and condensation, a wind that blows toward the darkness and simply disappears. Then dawn comes. The first rays of sunlight touch the frozen plains of the night side, and the process violently reverses. The fresh, delicate frost, now exposed to solar heating, does not melt. In the vacuum, it sublimates instantly, transforming from solid ice back into a gas in an explosive rush. The atmosphere is reborn not from volcanoes in that moment, but from the ground itself, as if the very surface is exhaling. This daily cycle of collapse and rebirth makes Io's atmosphere the most ephemeral in the solar system. It is an atmosphere with a lifespan measured in hours, a transient shroud that must be rebuilt from scratch every single morning. This incredible process underscores the total dominance of external forces over this moon. Its air is not a permanent, buffered system like our own, but a fleeting phenomenon, a ghost that appears with the light and vanishes with the dark, forever trapped in a diurnal dance between the sun's warmth and the absolute cold of space. That daily collapse of atmosphere is a direct consequence of a far greater force, the relentless cosmic engine that drives every single strange phenomenon on this moon. The ultimate architect of Io's fire is not found on its surface, but in the invisible gravitational dance it performs with its giant parent and its sibling worlds. This is the phenomenon of tidal heating, a process so powerful it can melt a planet from the inside out. To understand it, picture a simple ball of clay. Now imagine holding that ball in one hand and squeezing it rhythmically, first from the sides, then from the top and bottom. The clay does not just change shape, it warms in your hands from the internal friction of all its particles rubbing against each other. Now replace your hands with the gravity of the largest planet in our solar system, and replace the rhythmic squeeze with an orbit that is constantly being pulled out of perfect circularity by two other massive moons. That is Io's reality. Jupiter's immense gravity exerts a phenomenal pull on the side of Io facing it. But because Io is also locked in a precise orbital resonance with Europa and Ganymede, its path around Jupiter is forced into a slight ellipse. This means its distance from the giant planet changes constantly throughout each orbit. When Io is closer, Jupiter's pull is stronger, stretching the moon toward it. When Io swings farther out, that pull relaxes slightly, allowing the moon to settle back into a more spherical shape. This constant, rhythmic stretching and relaxing is not a surface effect. It flexes the entire world deep into its mantle and core, like bending a metal coat hanger back and forth until it grows hot to the touch. On Io, the friction generated by this planetary scale flexing is unimaginable. Rock grinding against rock, layer sliding against layer, all under pressures that crush atoms. This friction is converted directly into heat, and on Io, there is no escape valve for this energy except through the crust. The heat builds and builds until it exceeds the melting point of silicate rock. But this is not a localized melting. The tidal forces work on the entire moon, creating a vast global reservoir of partially molten material, a slushy ocean of magma that churns beneath a thin, brittle shell. This is the fuel for every volcano, the source for every lava lake, the pressure behind every plume. Without this ceaseless gravitational kneading, Io would be a cold, dead world like our own moon, its internal fires long since extinguished. The tidal heating engine is so efficient that it can melt rock on a planetary scale, turning Io into a volcanic powerhouse that outshines Earth. It is a reminder that the most spectacular landscapes in the cosmos are often forged not by internal chemistry alone, but by relationship, by the invisible and unbreakable bonds of gravity that tie worlds together in a dance of creation and destruction. But this invisible engine of gravity does more than just heat Io. It directly connects the moon's fire to a cosmic electrical circuit of staggering scale. The sulfur dioxide gas erupting from volcanoes like Peel is not merely a local spectacle. It becomes the raw fuel for one of the most brilliant features in the Jovian system. As this gas escapes into space, it forms that tenuous, temporary atmosphere. But Io orbits within the jaws of a monster, Jupiter's immense and rapidly rotating magnetic field. This field sweeps past Io at a relative speed of over 50 kilometers per second, a supersonic gale of invisible force. The neutral sulfur and oxygen atoms in Io's atmosphere are caught in this flow and violently sandblasted. High-energy particles from the magnetosphere slam into them, stripping away electrons in a process called ionization. In an instant, a peaceful atom is transformed into a charged reactive ion. Now electrically charged, these particles are no longer free. They become ensnared by the magnetic field lines, trapped like iron filings around a magnet. Billions upon billions of these ions are picked up and accelerated, whirled around Jupiter at tremendous speeds. Collectively, they form a donut-shaped ring of superheated plasma that traces Io's entire orbital path, a glowing halo of lost atmosphere known as the Io plasma torus. Seen in ultraviolet light, this torus is one of the brightest objects around Jupiter, a direct and luminous byproduct of volcanic fury, but the connection is even more intimate. This torrent of charged particles does not just orbit passively, it rains back down on Io itself, because the Moon is tidally locked, always showing the same face to Jupiter. One hemisphere constantly leads in its orbit while the other trails. The trailing hemisphere bears the brunt of the assault. It plows directly into the flow of magnetospheric plasma, like the back of a speeding car driving through a hailstorm. This relentless bombardment has a sandblasting effect on the surface, a process scientists call sputtering. High-energy ions smash into the frozen sulfur dioxide frost and colorful sulfur deposits, knocking individual atoms and molecules loose with the force of their impact. These sputtered particles are ejected into space, where they can either escape entirely or form an extremely thin global haze, a secondary atmosphere even more tenuous than the volcanic one. This constant erosion acts as another artist on Io's canvas. It may help explain why some regions appear uniformly bright or dark, as the sputtering process selectively removes certain chemicals or alters surface textures over time. More profoundly, this two-way exchange makes Io an active component in Jupiter's space weather. The Moon is not a passive rock being pummeled, it is a factory injecting fresh fuel. The ionized volcanic gases directly into the giant planet's magnetospheric engine. This fuel influences the intensity of radiation belts, fuels spectacular auroras at Jupiter's poles, and creates complex electrical currents that flow between the Moon and the planet's atmosphere. A single eruption on Io's surface can, within days, alter the particle population in a magnetic domain billions of times larger than the Moon itself. The volcanoes are not just geological features, they are pistons in a machine that spans millions of kilometers, a machine where a moon's breath becomes a gas giant's light show, forever linking the fire below to the storms above in an endless electrified dance. This electrified dance of particles and plasma begins with the very rock that erupts from the depths, but for decades, a fundamental question burned at the heart of Io science. What exactly is flowing across its surface? Is it familiar rock or something far more alien? The search to distinguish between active silicate and sulfur lavas has been a detective story written in infrared light and color, a debate that reveals a world with two distinct kinds of fire. The strongest evidence points to lava as hot as the forge of creation itself. Infrared telescopes and spacecraft have measured temperatures at eruption sites exceeding 1,600 degrees Celsius, a searing heat that can only be explained by one thing. Silicate rock. This is the same family of material that makes up the black basalt of Hawaiian volcanoes or the continental crust beneath our feet, but on Io it may be an even more primitive, scorching variant. At such extreme temperatures, sulfur or its compounds would simply vaporize. They cannot exist as a liquid flow. These ultra-hot measurements, particularly from outburst eruptions and vast floods like Patera, are the smoking gun for silicate volcanism. They tell us that Io's tidal engine is so powerful it can melt the deep, rocky mantle and bring that primordial liquid rock surging to the surface, creating rivers and lakes of a material we would fundamentally recognize, if not in its unimaginable scale. Yet for every rule on Io, there seems to be a brilliant, colorful exception. Alongside these infernal silicate floods, scientists have long suspected the presence of a cooler, stranger kind of lava. The evidence is in the landscape itself. Some flows display peculiar morphologies that don't quite match rocky lava. They can appear incredibly thin and widespread, almost like a paint spill with remarkably smooth, flat surfaces. Others show fantastically bright, vivid colors, lemony yellows, deep oranges, and fiery reds that change over time. While radiation can stain silicate rock, these rapid and intense color shifts hint at a surface that is chemically active in a different way. This is where sulfur enters the picture. elemental sulfur, when pure, melts at a relatively low temperature, around 115 degrees Celsius. Imagine a world where the very ground can melt from a modest geothermal warmth, not a cataclysmic fire. A flow of molten sulfur would behave unlike any lava on Earth. It has a bizarre property. As it heats up, its viscosity changes dramatically. Warm sulfur lava is thin and runny, but as it gets hotter, its chains of atoms break apart and it actually becomes thicker and more viscous. This could create flow patterns that are impossible for silicate rock, with sudden changes in texture and speed based on tiny temperature differences. The most compelling visual case might be a volcano like Sobo Fluctus. This immense flow field has a peculiar, mottled appearance of bright reds and oranges, and its thermal signature is significantly cooler than the silicate powerhouses. While not definitively proven, its behavior and appearance fit the profile of a vast, slow-moving flood of molten sulfur, perhaps oozing from a vent that taps a shallow crustal reservoir rather than the deep mantle. The color changes here could be a direct thermal map. As the sulfur flow cools and solidifies, it forms different allotropes or molecular arrangements, each with its own distinct color. A flow could start as a pale yellow liquid, darken to orange as it cools and thickens, and finally solidify into a brittle brick-red crust, all within a single advancing lobe. This would create a living palette on the ground, a real-time chemical clock ticking with the flow's temperature. So who wins the debate? The answer is that Io, in its infinite strangeness, refuses to choose. The evidence is overwhelming that it hosts both kinds of volcanism simultaneously. This makes it a doubly strange, doubly fascinating world. In one hemisphere, a titanic fissure might be tearing open, vomiting a curtain of incandescent silicate magma 1,500 degrees hot into the black sky, a direct conduit to the moon's searing mantle. 1,000 kilometers away, a gentle, persistent vent might be oozing a slow, oily river of golden sulfur, painting the cold plains in a slowly spreading stain of color. This duality means Io's surface is not just a battleground between creation and destruction, but between two entirely different languages of geology. It possesses the familiar, rocky volcanism of terrestrial planets, turned up to an 11, but it also hosts a kind of cold, chemical volcanism more akin to what we might expect on the icy moons of the outer solar system. It is a hybrid world, a place where the deep fires of a rocky body and the shallow chemistry of a volatile, rich crust meet at the surface, creating a volcanic repertoire unmatched anywhere else we know. This coexistence forces us to expand our definition of what a volcano can be, and to accept that on this moon, the palette of destruction comes in every temperature and hue imaginable. This dual nature of volcanism raises a profound question about the world itself. Do Io's countless fires burn in isolation, or are they whispering to each other across the frozen plains? The concept of volcanic triggering proposes a startling possibility that a cataclysm in one hemisphere could literally set off an eruption in another, linking the moon's fury in a single, trembling web. Given the global nature of the tidal forces squeezing Io, it is a hypothesis that demands serious consideration. The entire crust is under immense, fluctuating stress, a thin shell stretched over a churning ocean of magma. When a massive outburst eruption occurs, like the collapse of a giant magma chamber roof, it is not a local event. It is a geological earthquake of the highest order, one that would release staggering pent-up energy and critically redistribute the weight of the crust itself. Picture a frozen lake covered in a sheet of ice. If you strike the ice in one spot with tremendous force, creating a massive hole and sending shockwaves through the entire sheet, you might see cracks radiate outward and distant, weak points in the ice might suddenly give way. On Io, the ice sheet is the silicate crust and the strike is a super eruption. The sudden removal of millions of tons of magma from a subsurface chamber would cause the ground above to collapse, altering the local gravitational field and the strain patterns in the surrounding rock. Seismic waves from such an event would race around the entire globe, shaking every mountain and caldera. This global shudder could be enough to destabilize other volcanic systems already on the brink. A distant magma pocket, pressurized and ready to burst but held in check by the confining pressure of the surrounding rock, might find that the passing seismic wave provides just the final nudge it needs. The wave could fracture a last, thin barrier of rock or agitate the magma, causing gases to come out of solution and increase pressure instantly. In this scenario, one volcano's climax becomes the starting gun for another. However, proving this communication is extraordinarily difficult. Eos volcanic activity is so constant and widespread that distinguishing a true trigger from a simple coincidence of timing is a monumental statistical challenge. With dozens of volcanoes active at any given time, two major events happening within days or weeks of each other could easily be random chance in a system of perpetual chaos. Yet, some tantalizing patterns have emerged from long-term observations. There are hints, though not conclusive, that periods of exceptional activity at one of the major supervolcanoes like Loki Patera sometimes correlate with increased thermal emissions or new plume sightings elsewhere on the Moon. It is as if the planet takes a deep, strained breath and then exhales from multiple vents at once. This leads to the grander, more speculative vision of Io not as a collection of independent vents, but as a single, integrated organism. Its tidal heated interior is the beating heart. The worldwide network of fractures, catenae, and faults are the circulatory system, and the volcanoes are the pores, the release valves where the internal pressure finds escape. In such a model, the entire system could have a rhythm, a planet-wide pulse where stress builds, is released in a cascade of eruptions, and then slowly rebuilds. The volcanoes would not be independent actors, but players in a global symphony conducted by the gravity of Jupiter, their eruptions the notes in a song of strain and release. Whether this interconnectedness is a rigid chain of cause and effect or a looser, resonant harmony remains one of Io's deepest mysteries. It asks us to see the Moon not as a static landscape dotted with fires, but as a living, trembling whole, where an event on the far side of the world might begin with a whisper felt through the very rock beneath your feet. The true interconnectedness of Io's volcanic web is a mystery we can only solve from afar, a puzzle whose pieces are scattered across 1 million square kilometers of alien fire. For decades, our knowledge has been built from fleeting flybys and distant telescope glimpses, a portrait painted in broad, blurry strokes. But the next chapter in this story promises a revolution in clarity, a leap from grainy snapshots to a living, breathing, three-dimensional map. The future of Io science hinges on a dedicated mission, a spacecraft designed not to race past on its way to other worlds, but to stay, to watch, and to listen. Imagine an orbiter equipped with a suite of instruments we can only dream of from Earth. High-resolution stereo cameras would capture the surface in breathtaking detail, allowing us to construct a precise topographic model. We would no longer just see a dark flow, we would measure its exact thickness, trace the steepness of its levees, and watch in real time as a new lobe advances by mere meters per day. This three-dimensional view would transform our understanding. We could finally determine the true volume of colossal features like the Masubai flow field, settling debates about how much lava this moon truly produces. We could watch the migration of hotspots within Planetary like Loki, not as an inference from thermal data, but as a visible, crawling change on a digital landscape. Every mountain, every fracture, every caldera rim would be rendered with the fidelity of a satellite image of Earth, revealing textures and structures completely invisible to us now. But the vision goes beyond sight. A dedicated mission would carry advanced thermal mappers, instruments capable of monitoring the entire globe continuously, not just in brief flyby windows. We could watch the daily pulse of the atmosphere freezing and sublimating. We could track the cooling curve of a new eruption from its first incandescent hour to its final thermal echo decades later, building a perfect library of volcanic behavior. Most critically, we could perform the definitive accounting of Io's heat flow. By measuring the infrared output of every single black spot, lava lake, and flow with unprecedented precision, we could finally close the book on the global heat flow paradox, determining once and for all if our models of tidal heating are complete or if a deeper, hidden source of energy churns within. The orbiter would also act as a seismic monitor in space. By tracking subtle changes in the Moon's gravitational field as magma shifts in vast underground reservoirs, we could essentially perform a sonogram of Io's interior, mapping the size and depth of its magma ocean for the first time. Yet for all an orbiter can teach us, the ultimate dream, however distant, is to touch the fire. The concept of an Io lander is a staggering engineering challenge, a descent into the most hostile environment ever targeted for surface exploration. It would need to survive intense radiation, avoid constant volcanic bombardment, and find a stable patch of ground in a world that actively seeks to bury or melt anything that rests upon it. But if such a miracle were achieved, the scientific return would be transcendent. A lander's instruments could answer questions no orbiter ever could. A spectrometer could analyze the exact chemistry of the colorful surface deposits in situ, definitively proving whether a particular flow is silicate rock or solidified sulfur, ending that decades-long debate. It could taste the thin atmosphere, measuring its changing composition from sunrise to sunset, and directly sample the particles of frost that fall like silent snow. Most profoundly, a seismometer placed on Io's surface would open a window into a world of sound we can scarcely imagine. It would listen to the Moon's heartbeat. Every distant caldera collapse, every magma chamber rupture, every titanic landslide from a crumbling mountain would send vibrations through the global crust. This seismic network, even with a single station, could map the interior structure with clarity, pinpointing the depth of the magma ocean, locating active conduits, and perhaps even detecting the deep rumble of the tidal flexing itself. It could finally tell us if eruptions truly trigger one another by recording the seismic waves from a cataclysm on the far side of the Moon and watching for a responding quake beneath a nearby volcano. The data would be a symphony of creation and destruction played in real time. Every one of the 30 strange phenomena we have explored, from the wandering plumes to the radar bright flows, from the migrating hotspots to the global heat flow, is currently a hypothesis waiting for confirmation, a beautiful sketch awaiting the detail of a master's brush. We understand the outlines of Io's fury, but the mechanics, the chemistry, the intimate connections remain shrouded in inference and mystery. A future mission with its orbiting eyes and perhaps one impossible day, its listening ear on the ground, would transform these sketches into a high-definition film. It would turn Io from a distant, enigmatic torch into a known world, a laboratory where we can finally watch, in intimate detail, the relentless and beautiful physics of a planet being torn apart by gravity and stitched back together with fire. The greatest discoveries about this volcanic forge are not behind us. They are waiting in the data stream of a spacecraft that has yet to be built, in the first close-up image of a lava lake's churning crust, and in the first seismic tremor recorded on a world where the ground never, ever rests. The final and perhaps most profound of Io's strange phenomena is not a plume or a lava lake, but the role it plays in our cosmic imagination. This tortured moon is more than a spectacle. It is a time machine and a template, a working model of planetary extremes that allows us to peer into the past of our own world and imagine the fires burning on distant ones. Its relentless volcanism offers us a unique window into a chapter of Earth's history that is forever lost to us, a time when our infant planet was a far more violent and energetic place. Shortly after its formation, Earth's interior was seething with the residual heat of accretion and the intense radioactivity of short-lived elements. This primordial furnace drove a global volcanism that likely dwarfed anything we see today, with magma oceans, planet-spanning lava floods, and an atmosphere perpetually choked with volcanic gases. That Earth is gone, its fiery youth cooled and buried under billions of years of plate tectonics, erosion, and life. But on Io, that state of hyperactive, heat-driven resurfacing is not a memory, it is the present. By studying the mechanics of Io's global magma ocean, its efficient tidal heating, and the way it rapidly recycles its entire surface, we are watching a plausible, scaled-down version of our own world's hellish infancy. Io shows us what a rocky planet looks like when its internal engine is cranked to the maximum, providing critical clues about how Earth's crust first solidified, how its early atmosphere was forged in volcanic vents, and how quickly a world can remake itself from the inside out. Yet Io's relevance stretches far beyond our own solar system's history. It serves as a vital template for understanding worlds we are only beginning to discover. Astronomers have now found thousands of exoplanets, and among them are likely many hot Jupiters, gas giants orbiting perilously close to their stars. Just as Jupiter's gravity squeezes Io, the star's gravity would squeeze these giant planets, but it could also ignite any rocky moons they might possess. An Io-like moon in such a system would experience tidal heating on a scale we can barely conceive, potentially becoming even more volcanic, more incandescent than the moon we know. Furthermore, we are beginning to find rocky exoplanets in ultra-close orbits around smaller stars, worlds where gravitational tides could also stretch and heat their interiors to a breaking point. Io is our only nearby example of what such a tidal volcano world might be like. Its study teaches us what signatures to look for in the light of distant stars. The periodic brightening of a lava lake like Loki, the sulfurous spectral fingerprints of a giant plume, the specific infrared heat signature of a global magma ocean, these are all phenomena we can now model and search for in exoplanet data. Io provides the decoder ring, showing us how extreme internal heating manifests on a planetary surface. It transforms from a Jovian curiosity into a universal reference point, a Rosetta Stone for interpreting the volcanic potential of locked, stressed worlds across the galaxy. In the end, Io's 30 strange phenomena coalesce into a single, monumental lesson. It demonstrates the incredible, transformative power of gravitational relationships. A moon that should be cold and dead, given its distance from the sun, instead burns brighter than any world in our system because of the invisible embrace of its giant parent. It proves that a planet's character is not dictated by sunlight alone, but by the complex dance of forces within a stellar family. Io is a laboratory of extremes, a place where we witness the raw, unfiltered processes that build and destroy worlds. Every eruption is an experiment in planetary physics, every lava flow a testament to the energy that binds the cosmos together. By understanding this single, fiery moon, we gain the vision to see the hidden fires of the past and the distant flames of countless other worlds, forever linking its local fury to the universal story of creation. From the rhythmic heartbeat of Loki Patera to the silent, wandering plumes that appear from nowhere, our journey across Io has been a tour through a reality where geology operates on a scale of pure myth. This moon forces us to abandon every comfortable assumption we carry from our own world. Here, mountains are thrust upward by global compression only to be sandblasted into dust, rivers of molten rock flow for centuries, and the very air is a temporary ghost exhaled by volcanoes and frozen each night. The paintbrush strokes of Peele's red ring, the explosive meeting of lava and frost, the cryptic radar bright flows that may be samples of the moon's primordial heart. Each phenomenon is a chapter in a single story, the story of a world being cooked alive by the gravity of a giant. Io stands as a permanent challenge to our Earth-centric view of planets. It proves that stability is not a default, but a rare and temporary condition in a universe built on dynamic, often violent change. The beauty of our solar system is not found in calm, blue marbles alone, but in these forges of chaos, these laboratories of extreme physics that show us just how creative and destructive cosmic forces can be. So we turn the question to you after witnessing these 30 strange wonders. Which one captured your imagination? Was it the predictable pulse of the solar system's largest lava lake, or the silent, creeping advance of a river of fire longer than any on Earth? Share your thoughts in the comments below, and if you want to join us for more journeys into the deepest corners of space mystery, be sure to like this video and subscribe to the channel. The cosmos is full of stories waiting to be told.